السلام ورحمة الله وبركاته.
حياكم الله يا اخوان. Today my computer, alhamdulillah, most likely today is going to be the last class, but my computer today is really upset with me because I've been using it since about 7 a.m. and usually I give the lecture from office. Today I'm at home, and at home I don't have that cooling fan. I usually have a small cooling fan that cools it. I don't have it at home, but apparently the computer has overheated. Well, and the screen is flickering and so on. But inshallah it will work. I gave the last class for the other course while it was doing this. So alhamdulillah, مش الحال. Okay. طيب, so hopefully inshallah today will be the last lecture, meaning طبعا next Sunday I will give you only a quiz, and I haven't decided on the material of the quiz yet, but it will be some of the old material, probably about the Fourier transform. I told you that I will give you quiz number 5, which I will decide on later today, inshallah. And quiz number 6 will be on the Laplace transform. I already recorded 2 lecture notes, the makeup lecture notes. So what I want you to do, if you haven't watched them, watch them. And quiz number 6 will be take-home quiz. Inshallah, I'll put it for you later today or tomorrow at most. Okay, and I'll give you 3 days maybe for it. And I'll ask you to bring quiz number 6 probably Monday at night or so. So you'll have plenty of time. It will be more or less like a homework, maybe 3 or 4 problems about the Laplace transform, just to make sure that you watch those lectures. Okay, fine. So, and I'll decide on quiz number 5. Inshallah, I'll decide on it later today. Let me just think exactly what I will ask, what is the material, and I'll communicate it to you through WhatsApp. So last class, ya ikhwan, we talked about, or last few classes, we have been talking about discrete time systems and so on. And I think I mentioned even at the beginning that whenever we talk about discrete time systems, the transform that we will use, it will be called Z transform. It's not the only transform that we can use, but it's the transform that is typically used for discrete time systems. Okay, so let's talk about the Z transform. By the way, the lecture notes are almost complete. Yesterday, I spent 3-4 hours completing them. I added a lot of figures here and there, and I added a lot of discussion about the Z transform. So I just need maybe to check something here and there, and probably then I will upload them, and that's it. This will be the complete set of lecture notes, and you will only be responsible for whatever is in the lecture notes. So let's start discussing the Z transform. Now, what is the Z transform? The Z transform is given by this formula. And as you see, inshallah, it's typically easier to find the Z transform than to find other transforms. This is basically the Z transform. And we said that sometimes the Z transform can be represented because the Z transform is applied on discrete time signals. So sometimes you can represent the Z transform as a series of samples. This way. You cannot do this with the Laplace transform or Fourier transform. But with the Z transform, you can generally write the Z transform. Sometimes if I give you a signal, I can find the Z transform almost immediately without without thinking about this. What is the concept of the Z transform? It says that if you have a signal with some samples, and I'm talking in here about what we call the unilateral Z transform, which means Z transform only from 0 upwards. I'm not considering Z transform of signals that have components on the negative side and on the positive side. I'm talking about the unilateral, not the bilateral. So assume that I have a signal that looks like this. And in here, at 0, I have something there, and something there. This is at 1, this is at 0, and this is at 2. I can immediately find, assume, for example, that this value is 2, this is equal to 1, and this is equal to 3. Okay? This is x of n. And someone asks you to find the Z transform, don't even worry about that formula. The Z transform there will be equal to 2. So x of z will be equal to 2. This is basically the value of the sample that exists at 0. Now, every other sample, you'll add its value. So this is I'm adding 1, which is basically the value in here. But I don't just say 2 plus 1 plus 3. If I do this, all of the samples are added together, and I cannot distinguish between the location, or let's say the location of the sample has disappeared if you add all of the values of the samples. So what is the Z transform? You add every sample and multiply it by Z raised to the negative power where the power of that z indicates the location of that sample. Meaning, this is the sample at 0, so I just add 2 multiplied by z to the power of 0, which is 2. Z to the power of 0 is 1. Anything to the power of 0 is 1. Yeah? So basically, the z transform is 2 for the first sample, and then the next sample has a value that is equal to 1 multiplied by z to the power of minus 1. This basically indicates the value of the sample, and this indicates its location. Its location is at location number 1, or let's say at sample location number 1. Add then 3, which is basically the value of this sample, yeah, multiplied by this, the location of this sample is 2. So it becomes z to the power minus 2. And this is basically the z transform. You see, it's very quickly, I can immediately get it. Now, if I had other samples, just add them like that. If this was given not as 3 samples, but if I gave you, for example, that x of n is equal to, let's say, for example, n squared multiplied by u of n. One option is to say that this is equal, for example, to plot those points. Yeah. At n equal to 0, I'll get 1. At n equal to 1, I'll get again 1. Sorry, at n equal to 0, no. 0, by the way, squared is 0. Sorry, 0. 0. Okay. 1 squared is going to be equal to 1. 2 squared will be equal to 4. 3 squared will be equal to 3 squared is 9, and so on. Okay. And then you can write the z transform becomes equal to 0 plus 1 times z inverse plus 4 z to the power of negative 2 plus 9 z to the power of minus 3, and so on. Okay, so this basically becomes the z transform. So what I'm trying to say, gentlemen, is that sometimes the z transform can be obtained, especially for simple signals, very easily without going into the formula itself. This formula itself is quite simple. It's the different samples, each multiplied by z raised to the power of negative of the location of that sample. Okay? And now we say that x of n and x of z form a z transform pair. Okay? Now, when we talk about the z transform, very often we have to talk about something called the Taylor series expansion. And I'll explain to you why we need this. You know that the sum of alpha raised to the power of n, if you sum it from n equals 0 to infinity, this basically becomes equal to 1 when alpha is equal to 0. Alpha is any value, okay? When I have there, alpha raised to the power of 0, which is equal to 1, plus alpha raised to the power of 1, alpha and to the power of 1, plus alpha squared, plus alpha cubed, and so on. Now, this can always be represented in a different form, which is basically 1 divided by 1 minus alpha. This, some people sometimes, in fact, say that 1 divided by 1 minus alpha can be expanded into this. So you can do it the opposite. This thing can be compressed or condensed to become equal to 1 divided by 1 minus alpha. Okay. Right? Now, this will become useful. Also, there's another Taylor series expansion, which is if I have n multiplied by alpha to the power of n, this has a slightly different format, which is alpha divided by 1 minus alpha squared. You see that those will become important when we talk about the z transform. So let me find the z transform of some functions, and then you see why those two properties are important. If someone asks you, find the z transform of the impulse function, you say, fine, let me just plug in the impulse function in here. Let me just plug in what did I do? Okay, let me plug in, and instead of x of n there, let me plug in the impulse. Yeah, and you see that the impulse, the z transform of the impulse is quite simple. In fact, because I want to go a little bit fast, I'm not gonna write. Okay, so the z transform of the impulse function is nothing but the sum from 0 to infinity of the impulse multiplied by z to the power of negative n. But any function, when you multiply by the impulse, what does the impulse do? It evaluates the function at the location of the impulse. This is true for continuous time as well as discrete time signals. And this impulse is located at 0, which means that all I have to do is just plug in for n in there to be equal to 0 in here. For n to be equal to 0, so I'll end up with z to the power of 0, which is equal to 1. This basically disappears. And the sum of all of the samples of in an impulse is nothing but 1. Remember that the impulse looks like this. So if I sum all of if I have the sum from minus infinity to infinity, let's say, of the impulse, I'll get 1. The sum of all of the samples of, for example, the step function will become equal to infinity. And what I'm trying to say, gentlemen, is that there is a difference between the sum from n equal, for example, minus infinity to infinity of u of n. Okay, this is not equal to the sum from n equal minus infinity to infinity of u of n multiplied by z to the power of minus n. This is the z transform. Clearly, when n is equal to 0 to infinity. And in here, n equal to 0 to infinity. This is the z transform. This is not the z transform. This is just the sum of all of the samples of the signal. Meaning, sum the value at 0, plus the value at 1, plus the value at 2, plus the value at 3, and so on. It happens that the impulse only has, the unit impulse has only one sample, which is at 0. So if you sum all of the samples of that impulse, you get 1. Okay? It's like the integration of the impulse, of a continuous time impulse is equal to 1. Okay? So basically, the z transform of the impulse is nothing but 1. So this is straightforward. And then what I did is I found the z transform of the unit step function. I applied the same formula. Now the unit step between 0 and infinity is equal to 1. So this basically disappears. I don't have it. The step function, the idea of the step function is that it limits for you the range of integration in the continuous time signals. And in discrete time signals, it limits for you the limits of, or it changes the limits of the summation. The limits of the summation are already from 0 to infinity. So basically, the step function in all of this range is equal to 1. So remove this. It has no effect. So you'll end up with the summation from 0 to infinity of z to the power of minus n, which if you expand it, it becomes equal to 1 plus z inverse plus z to the power of minus 2 plus z to the power of minus 3, and so on. This thing is exactly similar to this, except that alpha is equal to z to the power of minus 1. If you think about it, if you have placed every alpha with z to the power of minus 1, you get exactly this. Okay? Exactly this thing. Which means that this becomes equal to 1 divided by 1 minus z inverse. Using this, the Taylor series expansion theorem, let's say. Okay? Just multiply this by numerator and denominator by z, and you'll end up with z divided by z minus 1. Okay? And this is why the z transform of the step function u of n becomes equal to z divided by z minus 1. And now I can find the z transform of other functions, b to the power of n, for example, multiplied by step. Or I think a ramp. I have b to the power of, okay, yeah, this. And the next one is the ramp. What is the z transform of the ramp? They're quite simple. All of them are quite simple. If you do them and use this Taylor series expansion, you'll see that you can find the z transform of most of the functions. Now, if I had time, I would have also found the z transform of the cosine and sine and so on. But I didn't have time, so I stopped at this point. But now, you'll see, I'll show you, inshallah, a table in a few minutes, okay, that contains all of those z transforms. You do not need to memorize them, but all of those z transforms exist in the table. Right? Now, there's also a theorem or some properties of the z transform that says that are called the initial value and final value. Now, those are not really, in my opinion, they're not that very useful. Okay? But since the book talks about them and they're part of the course, I decided to talk about them. What are the initial and final values? It basically says that if you have the z transform of any function, if you have x of z, and you're interested in finding only what we call the initial value, which is, what is the initial value? What is x of 0? In time domain, I'm not talking about capital X of z, evaluated at 0. I'm talking about x of n, evaluated at n equal to 0. Okay? I can find x of 0, small x of 0, by evaluating the Laplace, not the Laplace, the z transform of the function. If you evaluate it at infinity, you get, if you evaluate the Z transform at infinity, you get what we call the initial value, which is x of 0, small x of 0. Okay? Now, I didn't put any examples there, but you can probably, if I come in here, for example, let me take this. If I wanted to find what is x of 0, all I know is that this is the Z transform of the signal. Okay? I know that this is the Z transform of the ramp. And someone asked me, and let's say, I didn't know that it is the ramp. Someone told me that this is the Z transform of a function. Can you tell me how much is that signal at n equal to 0? All you have to do is say, evaluate this at infinity, at Z equal to infinity. Now, at infinity, I'll have infinity in the numerator, and in the denominator, I will also have infinity. But in the denominator, I have 1 minus infinity and then squared. So this is something like infinity divided by infinity squared. Clearly, infinity divided by infinity squared becomes equal to 0. Okay? This is not infinity divided by infinity. It's infinity divided by infinity squared, okay? Which becomes equal to 0. And clearly, yes, the ramp at n equal to 0 is equal to 0. If you do the same thing for the step function, let me come to the step function. If you evaluate this at Z equal to infinity, what do you get? You get infinity divided by infinity minus 1, which is infinity. Infinity divided by infinity in this situation becomes equal to 1. If you use, what's the name of the formula? L'Hopital's rule. Okay? You see that this becomes equal to 1. Take the derivative of the numerator and the derivative of the denominator, you'll end up with 1 divided by 1. So it's equal to 1. And yes, that's true. The step function at 0 is equal to 1. Okay? So basically, this tells you, this gives you a way for finding what is the value of the function at 0, if you don't know what the function itself is, what is the time function is. Okay? Now, also, there's a final value, which basically allows me to find what is the value, what is the final value, what is the value of that function at infinity. The first one tells me what is the value of the function at 0. That's why it's called initial value. The second one tells me what is the value of the function not at 0, but at infinity. Now, what do you do? In this situation, you have to multiply the Z transform by Z minus 1 and then evaluate it at 1. Again, you multiply the Z transform by Z minus 1 and then evaluate it at 1. If you do this, you'll get the value of the function at infinity. Okay? And you can test it. I'm not going to do it, but you can test it on the previous two, for example. In fact, let me do it for this one. Okay? Let me do it for this one. If I multiply this by, we said Z minus 1. Okay? If I multiply it by Z minus 1, Z minus 1 will cancel with the 1 minus Z. There will be a minus sign somewhere outside. There will be a minus sign, and this will cancel. Right? Now, if I evaluate this at, we said, if I evaluate it at 1, what will happen? The numerator will become equal to 1, and the denominator will be 1 minus 1, which is equal to 0. 1 divided by 0 is equal to infinity. And yes, the ramp at infinity, how much is it? It becomes equal to infinity because it increases like this. So, discrete time, but it increases linearly. So clearly at infinity, it will become equal to infinity. Okay? So at least for those couple of examples that I have done, they are true. Now we have a table of Z transforms and Z transform properties. Okay? And I just listed for you something like 7 or 8 different what happened. I jumped down. Okay, those are basically tables of Z transforms and Z transform. Just give me a minute. Okay, those are tables of Z transforms. Okay, and those are tables of Z transform properties. Okay, just like the Fourier transform and the Laplace transform, we had exactly the same tables. The transforms were different, but the same concepts. Okay, we had a table of Z transforms on the left and a table of Z transform properties on the right. Why do we have those? Because sometimes I may ask you, can you find for me the Z transform, for example, of this? You tell me that it's equal to this. Then what if I had a shifted version of this? Okay? Then you have to use this Z transform property, Z transform pair, in addition to the property that tells you if you shift a signal in time, this is how its Z transform will look like. Okay, so those I'm not going to go into them, but those are basically useful tables that you'll use. And in the final exam, by the way, I'll give you all of those tables, and you do not need to memorize any of those. Those tables will be given to you, and I added in there. I added also the initial value and final value theorems for the Z transform. Now, the only thing that remains for us, more or less, is how do you find the inverse Z transform? I think one of you has a question. Do you have a question, gentlemen? Ask. If you have a question, ask.
Doctor, also the table for the Fourier transform will be given in the exam?
Yes. You do not need to memorize any of those. Now, I was just thinking, this means that I'll have to print for you at least 3 or 4 pages. 1 page for the Z transform, 1 page for the Laplace, 1 page for the Fourier transform, yeah, and maybe 1 page for formulas that I'll give you. And just like I gave you some formulas in the midterm exam, I would probably give you kind of a long list of formulas for the final exam, probably. Right? That will include certainly much more than what I gave you in the midterm exam. Now, this means that 4 pages I have to print for each one of you, and you're about 30 students. This means about 120 pages. So I'm not sure whether I'll give you all of the tables or not. But if I'm going to ask you find the Fourier transform of this signal, and I want you to find it using the tables will be given to you. Okay. So if I don't ask you, for example, about the Laplace transform, I may not give you the table for it. Or if I don't give you if I'm not going to ask you about the Z transform or Laplace transform or Fourier transform, I just may eliminate the table for that transform. But if I'm going to ask you, certainly the table will be given to you. Okay. Right. Now, what remains for us is to find the inverse Z transform. Again, the inverse Fourier transform, you cannot find it using a formula, an equation like this. Where's that formula that okay? Yeah, this is the definition of the Z transform. There is another formula that gives you x of n in terms of it's some integration, some circular integration. I don't know if you understand what the meaning of circular integration, okay? But it's some circular integration of z of not z x of z. Okay, this is extremely difficult, and my knowledge, by the way, about circular integrations was when I studied, I'm not sure, Math 201 maybe, or Math 2, I don't remember, 202 maybe, or something like this. Okay, I don't remember honestly what is the course, and we didn't even spend that much time in it. Right? I remember this also concept came to us in EE340. If you take EE340, you'll study this a little bit, right? But the concept is still vague in my mind, and I will have to review it to be able to do any integration of this form. Okay, so clearly this is not the way to go. How do you find the inverse Z transforms? Just like we did with the Laplace transform. You remember in the Laplace transform, the 2 lectures, if you have watched them, we had to do partial fractions. Okay? Now, in the Z transform, there is another method that is sometimes easier, but it doesn't give you the inverse Z transform for, let's say, you can use it only in specific situations. And I'll show you what the other method is. The other method is using what we call long division. Now, I hope that you already understand what long division is. Okay? Assume that I gave you the following. I told you, I want you to find for me the inverse Z transform of this. Z divided by Z minus 1. I didn't give you the table. Z divided by Z minus 1. Find, this is x of Z. I want you to find the inverse Z transform of this. And I didn't give you the table. Now, are you stuck? No. Let's say the thing that you can do is, you can do the following. You can say, well, let me do long division of this. What is long division? Let me think of this as the division of 2 polynomials. Okay? And based on this, let me divide. Z divided by Z minus 1. Okay, this is what you need to do, by the way. You need to order the polynomial such that the numerator has the highest order there and the highest order here. Okay, and you have to order them this way. This is how you need to do the long division. Let's divide. Z divided by Z is 1. 1 multiplied by Z minus 1 is going to give me Z minus 1. Flip the signs, minus, plus, and then add. Or maybe I need to remove the flipping of the signs. Let it as it was, Z minus 1, and then subtract. Z minus Z is going to give me 0. 0 minus -1 will give me 1. Well, I prefer that I flip the sign, sorry, because so that I don't want, because I'm afraid always that instead of subtract, I add. Okay? So let me flip the signs. So clearly the z will cancel with the -z, and then I'll end up with 1. Am I done? No. Let me continue. 1 divided by z is z inverse, isn't it? So plus z inverse. Now multiply. Z inverse multiplied by z. Z to the power of -1 multiplied by z to the power of 1 becomes 1. صح? Z inverse multiplied by z, they cancel each other. So I'll end up with 1. But I'm not done. Z inverse multiplied by -1 will be minus z inverse. Flip the signs. This was minus. صح? Okay? So change it now to positive. Subtract. 1 minus 1, cancel, and I'll end up with plus z inverse. Am I done? No. Continue. Z inverse divided by z plus z to the power of -2. Okay? Z inverse multiplied by, z to the power of -2 multiplied by z will give me z to the power of -2. And z to the power of -2, sorry, it will give me z to the power of -1. Sorry, z to the power of -1. Okay? And z to the power of -2 multiplied by -1 will give me minus z to the power of -2. Okay? Flip the signs. Add, those will cancel. So I'll get z to the power of -2. Okay? And now you can see the process will continue theoretically forever. Z to the power of -2 will be divided by z will be plus z to the power of -3. And now you can see probably the pattern. Plus z to the power of 4, -4, plus z to the power of -5, plus z to the power of -6, and so on. Now this basically is equal to this. See this? Those are equal. Let me just make them a little bit thicker. Okay. Let me just select the font size here, or this, okay. Maybe even thicker. Okay. So now I know that x of z in here, I can write it as, just have it, x of z is going to be equal to 1 plus z inverse plus z -2 plus z -3, and so on. Now, how do I find the inverse z transform? Once you write it this way, like a polynomial, it's not the ratio between two polynomials, then finding the inverse z transform becomes extremely simple. What is the inverse z transform of 1? It's 1. It's a sample. Sorry, or let me say it this way. Can you tell me what is x of n? Can you sketch what x of n is? First of all, I have 0 samples to the left. Now to the right, this basically represents the sample that is at 0, and it has a value that is equal to 1. This is 1 multiplied by z inverse. We said that the z inverse basically means this is the location of the sample that exists at n equal to 1 is equal to, or the value of the sample that exists at location 1 is equal to 1. This is the magnitude, and this is the location. So in fact, at 1, I have a sample that is also equal to 1. At 2, I also have a value or a sample that is equal to 1. At 3, I also have a sample that is equal to 1. At 4, I also have a sample that is equal to 1, and so on. What is this? Isn't this the step function? It is. So you see, this is one way of finding the inverse z transform of any function. Now, you can come to any function, by the way. You can take even this. And you see that if you do long division, now long division, the problem with long division is that it's long. You see, it took me I don't know, 6, 7 steps to find this pattern. Sometimes, unfortunately, the pattern cannot be seen. The pattern here was easy because all of those were 1, 1, 1, 1, 1, 1, 1, okay? And this was repeating. If you noticed, each time I was getting z to the power -2, and then z to the power -3, and then z to the power -4, and so on. If you don't get in the long division a pattern that repeats, the only thing that you could get is maybe the first 4 or 5 samples. You cannot continue forever. Either you need to take this thing and plug it into a computer that will find for you the long division until infinity, okay? Or you basically say that, based on the long division, I'll only be able to find the first 6 or 7 samples, practically. Okay? You understand the point here, gentlemen? again, let me just repeat it. If you use the long division, gentlemen, it will allow you to find the inverse Z transform. But the problem with using the long division to find the inverse Laplace inverse Z transform is that the long division, unless it shows you a clear pattern that keeps repeating, you may have to stop after, for example, doing the long division. You're doing 5 or 6 steps of the long division only. And this basically will allow you only to find the inverse Z transform for the first 5 or 6 samples. And find only the first 5 or 6 samples of the signal. If the pattern does not repeat. If the pattern repeats, yes. Once you figure out that the pattern repeats, خلاص, you can say that this means that the inverse Z transform is basically a signal that is constant, for example, or a signal that increases linearly, and so on. Okay? طيب. One of you has a question, please.
Doctor, is there any way other than the long division?
Yes. And I wanted to start with this long division, okay? Because I think it's sometimes useful if you wanted to find the first 3 signals, let's say, or the first 4 samples only. And you don't want to bother with Z transform tables and so on. You only want to find few of the terms, then use long division. Okay? It does not require you to have any knowledge in the Z. Let's say it does not require you to have the Z transform tables. Now we'll come to the other method. Okay? So your question is very valid. Now we'll come to the second method. Now the second method, you already know it. What is the second method? It's basically, so forget about this. This is the long division. The other method is using partial fraction decomposition. The Z transform, gentlemen, is almost similar to the Laplace transform. If you look in here, if you look at the Z transform, the Z transforms, let's say, that we have in here, they look not that different from the Laplace transform. I mean, what I mean by they look not that different, they are different, but they look like a polynomial over a polynomial. You remember when we talked about the Laplace transform? Unfortunately, I'm not sure that you have watched the videos, but I think unfortunately, I don't have the table of Laplace transforms in. Okay, just give me a minute. I think I have it in here. Yeah, I think in there I have the table of Laplace transforms. Yes. Okay, yeah, this is the table of Laplace transform. Look, the table of Laplace transforms has a polynomial in the denominator and sometimes also a polynomial in the numerator. Right? Some polynomial in the numerator, polynomial in the denominator. Okay, except that the Laplace transform is in terms of S, the Z transform is in terms of Z. But it's not that different in principle, in concept. Okay, so if I get any Z transform that is a polynomial over a polynomial, I can always decompose it into fractions. Okay? I can always decompose it into something that looks like this, or terms that are added or subtracted that look like those. Okay? So basically, this is the idea of the Z transform, the other method of the Z transform. What you need to do is you need to decompose any Z transform that I give you, any Z transform. If I give you a Z transform like this and ask you to find the inverse Z transform, you can use long division in here, by the way. Trust me, if you use long division, if you divide this, multiply those together, and then do long division, you'll be able to find the inverse Z transform. But if we don't want to use this, if you want to use, let's say, the more, I'm not going to say practical method, but if I want to use the tables, what would I have to do? I'll have to decompose this into using partial fraction decomposition. If you haven't watched the 2 lectures of the Laplace transform, please watch them, because clearly you'll have to use those in the Laplace transform and also in here. The same concept, exactly. The only difference is this. The Z transform, if you look at the tables, and I'm emphasizing it, I gave you 2 examples below. Right? The only difference is the Z transform, gentlemen, of most of the functions, of at least most of them, will look like Z divided by Z. The line is very thick in here. the Z transform will generally look like Z divided by Z minus 1, or Z divided by Z minus B, or something like this. Yani look like this, okay? So you have a Z in the numerator, Z in the numerator there, Z in the numerator. You have Z in most of them, okay? Now, the problem with the partial fraction decomposition is that it gives you, when you do a partial fraction decomposition, okay, the partial fraction decomposition, for example, of this, just give me a minute. Where is that example? Okay, if I come to this example, the partial what just happened? I jumped up. Where is it? Okay, this is the example. The partial fraction decomposition, gentlemen, of this will give you the following. It will give you something like some constant divided by each one of those. My apologies if you haven't watched those two videos. I'm assuming that you have watched them. If you haven't watched them, you'll have to watch them so that you understand what I'm talking about. Okay, the partial fraction decomposition of this, so that you can find the inverse Z transform, will always look like this: Z minus 2. For example, added to it B divided by Z minus 3. Now, if you look at this, it's a constant divided by Z minus 2. And this is also a constant divided by Z minus 3. Okay? Constant divided by Z minus 2 plus a constant divided by Z minus 3. This thing, when you decompose it, it will look like this. Trust me. Even if in here, if I have Z minus 6, or if I have only 6, whether I have a constant in the numerator or I have a polynomial, Z minus 6, for example, in the numerator, always the partial fraction decomposition will look like constant divided by Z minus 2 plus constant divided by Z minus 3. Now, if I go to the table, I do not have constant divided by Z minus 2, for example, or constant divided by Z minus 3. The Z transforms that I have in the table almost always will be Z divided by Z minus B, or Z minus A, or Z minus something. Okay? So even if I got that partial fraction decomposition, assume that I did the partial fraction decomposition there, and I ended up with 3 divided by Z minus 2 plus 5 divided by Z minus 3. This, I do not see a term that looks like this in this table. Look at all the whole table, you do not have something like this. However, if this was not 3, if it was 3Z, then you have something that looks like it, which is this thing, where the 3 becomes just a constant outside, and Z divided by Z minus 2 is exactly the same form of this, where B is equal to 2 in there. So I can immediately find that this thing has an inverse Z transform, which is equal to this, and the 3 simply comes in here. You understand the point so far, gentlemen? Again, let me repeat it, because this is very important. The problem with the Z transform table, gentlemen, is that it almost always has Z divided by a polynomial, Z divided by a polynomial, Z divided by another polynomial, Z in there multiplied by some other polynomial divided by a polynomial, and so on. Okay, so if you did the partial fraction decomposition of whatever Z transform I gave you, this problem with the Z transform that I give you will give you something like 3 divided by Z minus 2 plus 5 divided by Z minus 3. If you come to those two terms separately now, you do not see any term or any Z transform in the table that looks like them. So you're not going to be able to find their inverse Z transform. So what is the trick? Or the idea here is that you almost always have that Z. So what do we do? Let us find the Z transform, or let's say find the partial fraction decomposition, not of the Z transform, but of the Z transform divided by Z. Meaning this. I'll come in here, to this, you'll see that what I'm going to say now makes sense. Okay. Okay. I jumped again. Again, something happened. Okay. Very, very nicely. I'll touch it with my only 2 fingers because maybe my hand was causing. Well, خلاص, the computer is about to crash, I think. Let me do it again. Hopefully this it will behave this time. Okay. This is basically the trick that we will do, gentlemen. We will say, instead of doing, now the picture is not very clear on the computer. I assume that you are also seeing exactly what I'm seeing. I see the things in there, but it is kind of fuzzy. Okay, now it is clear. Do you see the my screen clearly, gentlemen?
Yes, doctor.
Yes.
Okay, good. Right? So this is the trick, gentlemen, and please pay attention to this because this is very important. Okay? The idea is, what if we found the partial fraction decomposition for x of z divided by z? Okay? What is x of z divided by z? It's this thing. This, think of it this way. This becomes equal to z divided by 6 divided by z multiplied by z minus 2 multiplied by z minus 3. Now, if I find the partial fraction decomposition of this, how will it look like? It will be something like the following: a divided by z. Z is a factor there. It's just like this factor and just like this factor, except that this factor, the first factor or the first pole, is z equal to 0, while the second pole is z equal to 2, and the third pole is z equal to 3. Okay? But nevertheless, z is just a factor of the denominator. Okay? So it becomes a divided by z plus b divided by z minus 2 plus c divided by z minus 3. Assume that I found those. I found what is a, what is b, and what is z. Okay? And just for the sake of argument, let's say that we found that x of z divided by z is equal, for example, to 2 divided by z, using the same concept exactly that we talked about when we had to do partial fraction decomposition. 2 divided by z plus 3 divided by z minus 2 plus 5 divided by z minus 3. Okay? Now here's the trick. Let's multiply the whole equation now by z. So what will we get?
Again, we assumed the values of the constants.
Yeah, I just assumed them, yes. Because it will take me now at least 10 minutes to find those. Okay, I just assumed them. Yes, you're absolutely right. Okay. In fact, I have the solution down there. Yeah, but I just assumed them there. I didn't even bother looking down. Okay, so those are just assumed. Okay, assumed. Assumed. Maybe I should have got them from the solution that is below. Right? I solved this last night. So now the idea is, let me multiply the whole equation by z. What will we get? When you multiply this by z, z will cancel with the z. So I'll get x of z. When you multiply the right-hand side by z, I'll get 2 divided by z multiplied by z, I'll get 2. And the 3 divided by z minus 2 becomes plus 3z divided by z minus 2. And the 5 divided by z minus 3, when you multiply it by z, you get 5z divided by z minus 3. This is 2. This is not z, by the way. This is 2. Okay? 2, in fact, I have its inverse. If you go to the table in there, if I have 1, its inverse z transform is delta of n. So if I have 2, it becomes 2 delta of n. Okay? If I have, where is the second one in here? Okay. If I have 3z divided by z minus 2, z minus 2, okay, 3z divided by z minus 2, and the table in there, I have, let me list this thing, I had 3, I think, z divided by z minus 2. So clearly the 2 is equal to the b. The z is already there, and this z is there. So the only thing that I have is 3 outside multiplied by b to the power of n, u of n, where b is this quantity, okay, which is equal to the 2. So I'll end up with 3 multiplied by 2 to the power of n, u of n, and so on. And you do this again for the second term or third term, I'm sorry, and that's it. Basically, this is how you find the inverse Z transform. Okay. Now, I have talked only in here about cases where I have simple, or let's say real non-repeated poles. If I have repeated poles, for example, this is in fact the second example that I gave you down there. So this is if I have repeated poles. The concept is exactly the same. I have a pole in here that is repeated. Let me find x of z divided by z. Okay, and then decompose this. I'll have, this means that I'll have z in there, so I'll have something like a divided by z plus b divided by the non-repeated pole, which is z minus 2, plus the repeated pole. I must have 2 terms for it. C divided by z minus 3 plus d divided by z minus 3 squared. If you don't understand what I'm doing here, you need to watch those 2 lectures in the Laplace transform, because the concept is exactly the same, okay? Except that over there it's s, and here it's z. Right? So I need to find a, b, c, and d. Once I find those, now remove the z from there, or basically multiply the whole thing by z, so I'll get a z in there, b z, c z, and d z. And then you'll find that all of those, this one, this one, this one, and this one, exist in the table. They exist in the table with some modifications, maybe. Okay, this is why, this is exactly what I did in here, and I solved it for you today. I would recommend that you go and solve those 2 examples. Okay, and basically I found the inverse Z transform of that signal. Okay? Now, clearly, why are we doing this inverse Z transform? Because now the idea is, if I give you x of n, this is the last thing that I'm going to say in this course, the last topic to say. I have about 12 or 30 minutes, which hopefully is going to be enough. If I give you x of n that is going into a system with an h of n, you can find y of n either in time domain by finding the convolution of those 2, meaning y of n will be equal to x of n convolved with h of n, discrete time convolution, which is often simpler than continuous time convolution. Right? But nevertheless, you have to find the convolution. Exactly the same process, and I'll do it, inshallah, on an example in this last topic. Okay, you can either do this, or you can say, let me take this, find x of z, find h, not x, let's see it in here. I have h of z, okay, and then y of z becomes equal to x of z times h of z. Okay. Once you find this, then I can take now this thing inverse Z transform. In here I have Z transform. Okay. Z transform in here. Also here Z transform. Okay. To come up with h of z. Once you find y of z, then you need to do inverse Z transform to come up with y of n. In the case of discrete time signals, sometimes it doesn't make that much difference. Whether you go do it in time domain or frequency domain, it's not that much of... and going to frequency domain sometimes does not save you much. And this is basically what I'm trying to do for you now, okay? And an example that will hopefully give you... I didn't solve this example, but maybe this is the last thing that you have in there, okay? I promise you I'll not add anything after that. But let me show you how we can do... In fact, this topic is time domain convolution versus frequency domain Z transform. So I'll compare between the 2. I'll do to you, hopefully, if I have time, I'll do to you the Z transform, give you something. I'll do it both in time domain and frequency domain. And you see that it's not that much of a difference whether you do it in this form or in the other form. Right? Now let's do it in time domain. Time domain. Right? In time domain, what do? I do convolution. And I know that in the convolution of n is equal to summation from I equal minus infinity to infinity, theoretically, okay, of x of I times h of n minus I. So what do? I put x of I as it is, okay, and then flip h of I, or let's say h of I, flip it, okay, and then shift it. Exactly the same concept. So let me sketch for you, and I made sure that the signals are not that difficult. Let me sketch for you x of n. In fact, let me take this thing, shift it to the side. Okay. Let me sketch for you the two signals there. طبعا this is 0 everywhere, okay? Except at n equal to 0, I have a value of 1. Okay? At n equal to 1, I have a value of 3. This is x of n. I have a value of 3 in here. And at n equal to 2, I have a value that is equal to minus 2. If you allow me, let me change this to 2. Okay? And the reason is I don't want to bother with negative values. Okay? But trust me, it will work even if I had negative values. Those are basically the 3 non-zero samples, and everywhere else I have 0. Yeah, this is 0, 1, and 2. Okay? This is x of n. And then if I want to do the convolution, I have to change this to I or k or whatever, some other variable. Right? Let me take h of n, flip it. First of all, let me sketch it. X of n is 1, 2, 3. This is 1, 2 in here, and 3 in there. So this is h of n. This is 0, 1, and 2, and 0 elsewhere. Okay? So I need to convolve those two signals together. What do I do to one of them? Let me take h of n and flip it. It doesn't make any difference here which one you take and flip. Okay? If I flip it, this is what I'll get. So this is h of minus n. Or let's say, first of all, I had h of I. Well, this is I. So now I have h of minus I. Okay? And then shift it by an amount that is equal to n to the left. So it becomes h of n minus I. Remember that this is the point n. Just like we did with the continuous time, it's just discrete time. And then shift it all the way to the left. Now, clearly, as I increase n, what will happen? 0, 0, 0 product until n equal to 0. The first interaction between the two will happen at n equal to 0. Now, this is quite simple because what happens in discrete time convolution? You are multiplying number from the first signal with a number from the second signal. So clearly, at n equal to 0, okay, the only interaction happens between this point, the blue point in there, and the blue point in here. Both of them are equal to 1. So here I have 1. Okay? The product of the two, and then when you sum, you end up with only 1. Okay? Now let me take this thing and shift it by 1 unit. When n is equal to 1. Now n is equal to 1. Meaning that this point now, I don't know if I can do this. No, sorry. Select this. I'm maybe being too lazy to delete it, and okay, if I move this there, okay, now the interaction clearly is between. So what did I do? The interaction is between two samples. This has a value that is 1. This is 3. Remember, and this is 2. This has a value that is equal to 1, 2, and 3. So I have now the product 1 times 2, which is 2, plus 1 times 3, which is 3. So 5. Add the 2, you get 5. Okay? Now let me shift again. This is for n equal to 1. Let me shift again. Now in here, how much do I have? Okay, I have 3 times 1, that's 3. 2 times 3, which is 6, so that's 9. And 1 times 2 is 2, so that's 11. Okay, so remember the number, it was 11. Okay, and then I'll shift more there. So because I do not want to unselect those, so remember at n equal to 2, the answer was 11. Okay. Now I have 3 times 3, which is 9, and 2 times 2, which is equal to 4, 9 and 4, 13. 11 and 14. 11 and 13, I'm sorry, 11 and 13. Okay. And the last case, 6. Okay, for n equal to 5, I think I have 6. So now I can write this. I had 11. I think we said 13, and I think 6, if I'm not mistaken. This is at n equal to 2, at n equal to 3, and at n equal to 4. I think 1, 2, 3. Yes. Okay. And then for all values of n that are either less than, yani n equal to -1, it's 0. N equal to 5 is 0. 0 all the way there, and 0 all the way there. Okay? So now I found the convolution. This is how you find the convolution in discrete time. Let's see. Let me find now the Z transform and show you that it's not going to be that different. Especially for this signal, it's not going to be that different. Why? What's the Z transform of x of n in here? Let me just let me erase everything. Just give me a minute. Let me erase this mess. Anybody knows the Z transform? Anybody can tell me what the Z transform is?
It's the delta.
La, what do you mean delta? This we wrote this as 2, by the way. What do you mean by this delta? La, Z transform is you take each sample and you multiply it by Z raised to the power of its location. This is at 0. Okay, so it's basically x of Z will be 1, exactly 1. What about the second sample?
3z to the power -1.
You're absolutely right. 3. You're absolutely right. 3 z to the power of -1. And the next one?
2z to the power of -2.
Absolutely right. Yes. Okay. Let me do the same thing for h of n. So h of z will be equal to, I'll write it very quickly, 1 plus 2 z inverse plus 3 z -2. Okay. Now I found x of z and h of z. Yeah, if you have a question, ask.
Doctor.
Yes.
The location in N2, does it affect the z here? Z to the power of 1.
Oh, into, you mean this?
H of n. No, H of n.
Yeah, okay. Yeah, I just noticed it, by the way. I just noticed it. Yes. Honestly, I wrote the example, but I didn't solve it, and I just paid attention to the fact that this is 4. Honestly, wallah, just before you said it, I looked at that 4. Right? My apologies. What I meant there, or what I wanted to do in there. Okay. I remember when I wrote this example, I wanted to solve something that was kind of slightly more complicated, but I solved it based on 0, 1, 2. My apologies for this. Okay, I solved it based on 0, 1, 2. But it would still work even if I had 1, 2, and 4, but it would be slightly more complicated. My apologies for this. This clearly, yes, the values that I had before. Okay, this will make the Z transform, capital H of Z, will be equal to 1. Z to the power of -1 plus 2 Z to the power of -2 plus 3 Z to the power of -4. Okay, but clearly the solution that I have there with the convolution was not using this. Thank you so much for pointing this out. My apologies. I meant in there, or at least the one that I solved there was 0, 1, 2. Okay, because now I cannot change the convolution from do the convolution from scratch. Right? So now, assume that this is the problem that I have. What is x of z multiplied by h of z? X of z multiplied by h of z. You see, this is basically polynomial multiplication. You'll have to take those polynomials and multiply them. In fact, let me do it this way. Let me multiply. Okay? So this is basically y of z. Okay? I have 1 times 1 is 1. let me take the 1 in here and multiply by the whole thing. So I have 1 plus 3 z inverse plus 2 z to the power of minus 2. And then I'll take this term and multiply by the whole polynomial on top. 2z negative 1 multiplied by 1 is 2z negative 1. I'm not going to write it here. I'm not going to write it this way. I'm going to write it under this 2z negative 1 because at the end I have to add. So I have to be organized so that I can add the terms together. The terms with the same power of z, I have to add them together. If you allow me, I'll just take maybe 3 or 4 minutes. I promise you, because I don't want to bring you on Monday for a class just for this. Okay, Juan? Right. So 2z negative 1, and then I'll have plus 6z negative 2, and then this multiplied by that plus 4z negative 3. Okay? So this is the product of this with the whole thing on top. And then the last thing is 3z negative 2 multiplied by 1, so 3z negative 2. I put it under the z negative 2 terms, plus 9 z negative 3 plus 6 z negative 4, I think, if I'm not mistaken. Yeah. Now just add. You see that the first one in here is 1. In here I have 3z negative 1. And there I have 2 plus 6 plus, that's 9, 11. Z negative 2. And then I have 13, z negative 3. And I have 6, which are exactly the same numbers. Okay? Now the last thing that you need to do is take the inverse z transform. The 1 will result in this sample. So let me just highlight them. The 1 is basically this sample. Sorry, I was looking. This one exactly corresponds to this one. The 3 there. 3 is it? Sorry, 5. This should be 5. Yes, I got 5 in here because I have 2 plus 3. 5 corresponds to this. 11 corresponds to this. 13 corresponds to this, and 6 corresponds to the last one. So clearly, it gave us exactly the same answer. Okay. So basically, the idea of the z transform, I'll promise you this last thing. The idea of the z transform, gentlemen, by multiplying every value of the sample by z raised to the power of something, that z raised to the power of minus 2 or minus 3, it is preserving the location of that sample. Now, when you convolve that signal with another signal, or when you multiply the z transform, this term, for example, in the z transform from h with this term, and let me highlight them. This term in the z transform of x with this z transform in the z transform of h, this basically says that this sample is delayed by 2 units. This green in here, it says that this sample is delayed by 2 units. And this in h, it says that this sample is delayed by 1 unit. So the overall delay that results from multiplying those two, okay, becomes equal to 3. This is why the contribution of this, those two will have a component that exists at 3, at the location 3, and so on. And it's this. I have to add it with the contribution that results from this one with this one, because both of those also will contribute to the same sample at 3, and so on. And you might have other components. You might have this component from here with this component, and so on. There are different components that will all contribute to that same sample in time, in the output signal. Okay? So this concludes the lecture. I will not discuss anything else. This is basically the material that you are responsible for. The Z transform, because it comes at the end, and I have squeezed things, and I did not explain things, I think, in detail. I guarantee to you that the examples that I will give you will not be more complicated than the examples that you have in the lecture notes. Okay? I will not invent questions that are to challenge you in this material. Also in the Laplace transform, because I gave that material kind of recorded, okay? I will also make sure that the material that let's say the question that you will get in those two topics will be straightforward, just the same difficulty as the examples that you have in the lecture notes. Okay? Maybe different numbers or so, but they will not be more complicated. Okay, Juan? I'll see you inshallah Sunday, on Sunday, what I will do is I will only give you a quiz, and I'll let you know the material of the quiz for sure later today. Okay, Juan? And I'll upload the lecture note, inshallah. This lecture note, I'll upload it. Just give me maybe in an hour or 2 hours, it will be uploaded. Okay, maybe I'll solve this. I'm not sure if I'll solve this last example appropriately or not, but probably this is the thing that I may add to the lecture notes and then upload it. If you have any questions, please ask. If you don't have any questions, I'll see you inshallah on Sunday.
Okay, so we have a take-home quiz and a normal quiz.
Yes, a take-home quiz, which you'll submit to me probably Monday. I'll give you the deadline to be Monday, and a normal quiz on Sunday. The normal quiz, I'll let you know the material of it, inshallah, as I mentioned later today. The take-up quiz is on the Laplace transform, and I'll prepare the quiz, inshallah, also later today, maybe at night, and give it to you, and I'll give you 3 or 4 days to submit it.
Okay, thank you very much.
Sure, my pleasure.
دكتور وجيه،
تفضل.
عندي سؤال عن موضوع مهم، يعني أقدر أكلمك في التيمز.
طيب, does it have to be now, or can it be maybe later today?
أي وقت تبيه، بس اليوم أهم شيء، والسؤال خاص يعني.
طيب خلاص. Let's go right away. Anybody else has any comment or point? Anybody else has anything? Question, comment, anything you'd like to say?
ايوه دكتور